Let's welcome Jad, a friend of the family, speaking from Munich today, the Halimeh Munich, who has a wide range of interests, many of which overlap with some of our interests on quantum simulation, on equilibrium physics, on tensor networks in some flavors. And today's talk will bring together some of those ideas, as far as I can see, when he will be speaking about the stabilization of and engineering of exotic far from equilibrium gauge theory phenomena. So thanks for coming. I mean, that's what we can offer today, at least virtually. And yeah, the stage is all yours.
I'm very happy to be here. So thanks a lot for the invitation. And yeah, so basically, let me just set the timer. Good. So today, as Jens nicely introduced, I will be talking about the stabilization and engineering of exotic far from equilibrium gauge theory phenomena. So this is a fancy title that basically just summarizes what I've been focusing on over the last roughly 3 years. I've been focusing on stabilizing gauge theory implementations in quantum simulators. But at the same time, I'm interested in exotic out of equilibrium phenomena that we can get out of these implementations, out of these quantum simulations of gauge theories. So basically, as an outline of the talk today, I will be focusing on methods that we have devised to control and suppress errors that are unavoidable in quantum simulations of gauge theories. Number two, I will be talking about ergodicity breaking paradigms that you can find in these gauge theory implementations, that not only are they pertinent from a condensed matter point of view, like quantum many-body scars and disorder-free localization that Jens and Stephen and other members of the group know a lot about, but they're also pertinent from a high-energy perspective. So, for example, thermalization of gauge theories is still an open question. In heavy ion collisions, for example, there are indications that thermalization happens much faster than any relevant timescale, and there are some speculations that entanglement dynamics has something to do with this. So it's nice to be able to have these tabletop quantum simulators where we can probe these high-energy physics questions on them. I will also talk about the quantum engineering of exotic dynamics. So not only do gauge theories give us some exotic dynamics, as I will show you later, but you can, with simple experimentally feasible tricks, kind of enhance these exotic dynamics and make them amenable for use in quantum technology, such as quantum memories, for example. And last but not least, as you will see in all the work that we do, there's always a direct application to experimental realizations. So indeed, if you see here, I just sampled 4 of our many papers on this topic. The first 4 are theoretical papers, MPRL and PRX Quantum, where we basically developed the theories for a lot of the stuff that I'm going to talk about today. And the bottom 4 papers are experiments in which we led the theory. Basically, the theoretical works here where the schemes that we developed in them were nicely implemented in these experiments. And indeed, they stabilized the gauge theory over an extended period of time. Okay, so I've said gauge theory like a million times in this 1 minute. Let me motivate why we are interested in gauge theories. So gauge theories are fundamental frameworks of modern physics. You find them, you know, from general relativity to quantum field theory. It's really a very fundamental property of our universe. They implement laws of nature through local constraints. So for example, as you know from quantum electrodynamics, this would be the famous Gauss's law, right? It basically locally imposes an intrinsic relationship between your charge distribution and the resulting electromagnetic field. Now, quantum simulators offer us the chance of having a tabletop probe of high energy phenomena, you know, rather than, we're not saying we're replacing the Large Hadron Collider and setups like that, but these setups are really expensive. It's really hard to probe real-time dynamics in them. On the other hand, quantum simulators of gauge theories really allow you to calculate time evolution from first principles. So this is a big advantage that we would like to push forward and hopefully one day achieve 3+1 dimensional quantum chromodynamics on quantum simulators. We're still a long way from that, but we're hopeful. Also, due to the complexity of gauge theories, like I told you, there are all these local constraints. So you have to control your theory locally everywhere. This complexity allows us to see quantum simulations of gauge theories as a benchmark of quantum simulator technology. So one can be a little bit brave and say that if you can control a gauge theory in your quantum simulator, you can control a lot of generic quantum many-body models with less requirements. Let us put things on a bit of a more formal footing. So let us look here at the Schwinger model. The Schwinger model is nothing but quantum electrodynamics in 1+1 dimensions. So here you see the staggered fermions, psi, representing the annihilation and creation of electron-positron pairs. Now, interestingly, you see whenever you have a term as psi j dagger, psi j plus 1, which is a creation or annihilation of electron-positron pair, you see that you have in this term an additional operator u. This is the so-called gauge field. It's an infinite dimensional operator. And the job of this field is to act on the electric field E, such that whenever an electron-positron pair forms or annihilates, the gauge field changes the electric field in such a way that Gauss's law is preserved. Right, so here you have this electron-positron pair. Obviously, the electric field is going from the positron to the electron. But now if you flip them, if you move the electron here and the positron here, this electric field has to flip. And that's the job of U. U ensures that. Now, the generator of Gauss's law, this model has a U1 gauge symmetry. The generator of this symmetry is exactly what you see here. It's this guy, GJ, which basically is the difference of the electric fields on the links adjacent to site J, plus the matter configuration on site J. So if you look at it closely, you see that this is nothing but a discretized version of Gauss's law.
Can I ask you a question on at this point already?
Sure. Yeah.
So this model is of course ubiquitous. Like most talks that talk about lattice gauge theories have like this Schwinger model in 1+1D on one of the early slides, but it's always in 1+1D, right?
Oh, you can go to 2+1D. You can go to higher dimensions. That's no problem.
I see. That was basically my question. Like, to what extent the analogs in higher spatial dimensions would look identical?
That's a very good question. So actually, the interesting thing about 1+1D is it captures a lot of stuff from 3+1 QCD. That's why people are really interested in 1+1 quantum electrodynamics. So for example, here you have the topological theta angle. In 2 and 3 dimensions, you can integrate that out. It's no longer really topological. In 1+1D, you cannot get rid of it. And also this model has the so-called Coleman phase transition, which, to be honest, I am not sure if it changes its universality in 2D, but in 1+1D, it has the same universality as actual quantum electrodynamics in 3. So in the continuum quantum field theory limit. I suppose the reason why a lot of people in introductory talks look at 1+1D is because it doesn't include a nasty plaquette term, which is a 4-body term, and then you have to go into, you know, certain magnetic effects that don't really serve the purpose of introducing this model. But indeed, we are very interested in going to higher dimensions, and as I will briefly mention at the last of the talk, we're extending a lot of our works to 2+1D. So we have a paper that will come out in the next couple of weeks, which is a 2+1 implementation of this guy. Does that answer the question?
Absolutely. Wonderful. That's a full and complete answer. Thank you.
Thank you. All right, good. So now
I have a brief question.
Yeah,
so,
go ahead.
What do you mean by a generator of the Gauss's law, and how is this G related to the Hamiltonian here?
Okay, you have, as you know, you have certain transformations that leave your Hamiltonian invariant.
Okay,
right?
that generator, just making sure.
Generator.
Okay.
Exactly. That's all it is. It generates this U1 gauge symmetry. So it's not a global U1 symmetry like particle number conservation. It's actually local at every point in space and time.
Ah, okay.
Yeah. Good. And so now gauge invariance. So this model H0 is gauge invariant in that, and this relation is encapsulated in the following commutation relations that you see here. So H0 commutes with GJ at every point in space J, right? So again, so it's not like you're summing over J, it's not a global symmetry, it's really local. And gauge invariant states have the following property. So they're simultaneous eigenstates of all the generators GJ with eigenvalues small gj. And now if you take a collection of these eigenvalues GJ over the whole volume of your system, you define a gauge superselection sector. So you see you have an extensive number of superselection sectors, depending on how many eigenvalues your GJ can take. It's that to the power L, that's how many sectors you can have at most. And because the Hamiltonian is gauge symmetric, you can actually block diagonalize it in the basis of GJ. And now every block here that I pictorially represent as a yellow rectangle represents a specific, a unique super selection sector. And a lot of early experiments on quantum simulations of gauge theories tried to work in one sector, usually the sector where the eigenvalues GJ are zero everywhere. And this is what people call in the community the physical sector or the sector of Gauss's law. Many names, but they mean the same thing. So you just
but to be sure, like the model as such would kind of host the entire like structure of direct sums, right? It's just that one specific block would be singled out, but the Hamiltonian as such would of course incorporate them all. Is that correct?
Absolutely, absolutely. Yeah. And so numerically, what you do in exact diagonalization, like to be efficient, if you are only interested in one sector, you just build that sector, you forget about the rest. So the symmetry allows you to resolve these different sectors. You just go into one of them and you reach as big a system size as you want. And in experiments, what you try to do is you implement this sector as part of a bigger Hilbert space, which may or may not include the other sectors, as I will discuss in a little bit. Good. So what early experiments did is they tried to work in one sector and they approximated the infinite dimensional gauge and electric fields with spin S operators. So they were very modest and they started off with spin 1/2 operators. And one such experiment was from the Misha Lukin group, a very nice paper published in Nature in 2017. And what they noticed, they found something peculiar. So they saw that if you start in a certain state and you quench, you get coherent persistent oscillations well beyond relevant timescales. So as you can see, they tried it with 9 Rydberg atoms, 51 Rydberg atoms. They implemented this Ising-like Hamiltonian. And basically, they compared with MPS, and MPS more or less agreed with their experimental observations, and they couldn't explain this. Why isn't the system thermalizing? And it turns out that what's happening is this initial state in this specific model that they used is actually equivalent to the vacuum of QED. And when you do a resonant quench on that, so a quench with zero mass in the gauge theory that I showed you on the previous slide, what happens is your dynamics is stuck in a cold subspace of so-called quantum many-body scars. Now, these quantum many-body scars are eigenstates of the quench Hamiltonian that have anomalously low entanglement entropy and are equally spaced in energy. So what you see here is a pictorial representation of this. So just focus on the blue blob, and you see that the initial state, the vacuum psi naught, and its intersection with the eigenstates of the quench Hamiltonian shows you this equal spacing in energy. So your dynamics is kind of stuck in this cold subspace to significantly long times, and you don't normally see thermalization up to the accessible timescales experimentally or numerically for most applications. And in a recent theoretical experimental paper that we put out, which hopefully will appear in PRX soon, we showed that you don't have to start just in this state. Scarring is in fact ubiquitous. You can start in any initial state, and then I can tailor the quench Hamiltonian with a certain mass such that your initial state falls in a cold subspace of energetically equally spaced eigenstates with anomalously low entanglement entropy. And then the question here popped up. It's like, okay, maybe this is just an artifact of your regularization of the infinite dimensional fields with spin 1/2 operators. Maybe this is what's causing these scars, and they have nothing to do with gauge theories themselves. And we proved unequivocally.
But this is like sorry, you might say more about this later. But so are you saying that like well, maybe you will say more about this later, but my question on the high level is like, what property of the Schwinger model is it that makes it scar-like for arbitrary initial conditions? And also there was this work, nice work by my former student, Henrik Wilming, who looked at kind of certain, like he defined like properties of scarness and also looked at certain kind of recurrencies, and then could show that if you have certain types of recurrencies, then these properties of being like quantum scar-like, they have to be fulfilled. So I might ask now or later, to what extent these kind of properties of being quantum scar-like would be satisfied here. Oh, okay. Again, what is it that makes it scar-like?
That's a good point. So scarring basically in principle means that you have, if you look at the fidelity revivals, as you see here in this panel here, you get these periodic revivals that as you increase your system size in ED, they roughly converge up to a certain system size. I mean, in the thermodynamic limit, you expect them to completely go away, but you see that beyond finite size effects, they are there, right? So of course, I mean, you will always have some kind of revivals in a really tiny system if you choose a really tiny system. But when you have a scarred system, you go to system sizes where you still see these revivals, while other models, the revivals are completely damped. They're completely zero, basically. And what we call here scars are basically just these states. So we looked at their entanglement entropy, which I don't plot here, but we also looked at their overlap structure, and you see that they're equally spaced in energy.
Yes.
And we were able to relate these level spacings with the revival frequency. And what we were able to show here is if you do spin S representations of these fields in your Schwinger, in your regularized Schwinger model. So it's no longer the Schwinger model, right? We regularize it. The infinite dimensional fields become spin S operators.
Okay.
We show that as you increase S and you do proper finite size scaling, you see that your scars persist and the S goes to infinity limit, right? Which would be the Schwinger model limit.
I see.
But the caveat here is that you have to start in a so-called extreme vacuum. So basically, every spin S representation of the Schwinger model has 2S plus 1 vacua. So if you choose the most excited vacua, you will get scarring. If you choose the intermediate ones, you will get a bit of scarring, but it's much weaker. And so this is explained in detail in these two papers that will soon appear as a PRL plus PRB combo.
Wonderful. Okay.
Good. So now
sorry, may I ask a question before you continue?
Sure.
If I look at the first plot where we see the oscillations, how can I tell the difference between these oscillations, which, as you say, persist, with a typical plot of dynamics in a lattice system, like free fermions or any other model? I mean, what is you talked about oscillations well beyond relevant time scales. But I'm not sure what exactly you mean by timescales.
So the timescales are determined by the microscopic parameters of your Hamiltonian, right? So your interaction V and your drive omega. So these guys will set scales at which you expect the system to thermalize. So you won't have these persistent oscillations. They will be quite damped. And so you have some violent dynamics early on, but then they basically kind of dissipate. And you just have a steady state that has some really tiny oscillations, but nothing, you know, at this scale. And they show this in this paper. So in this Nature paper here with Bernian as first author, you actually see if they start in different generic initial states, basically, what generic means different than this one, you will see that basically they thermalize very quickly. You don't have these persistent oscillations that last for so long.
And in your plot, what is the system size of the MPS simulation?
So this is not an MPS. So that's their calculation, MPS. I'm not sure if they used infinite matrix product states or just, I don't know, a finite system. But basically, if I recall correctly, it was much larger than 51. So either it was infinite effectively in the thermodynamic limit or much larger than 51 atoms. So this is, you can consider this as the thermodynamic limit of this result. And it qualitatively agrees quite well. In our calculations here, we did we used exact diagonalization. So if you use, we have access to infinite matrix product states, but then you will not see any, like you can't calculate the fidelity, basically. This will just be zero. So instead we look at return rates. So we have a work coming up where we actually look at the return rate in the context of dynamical quantum phase transitions of these guys. And we answer some nice questions related to dynamical quantum phase transitions, not so much to scarring. But basically here, what the job of the MPS simulation was to show that what they are seeing was not a finite size effect.
Okay.
Good. So now I want to take you on a small detour to look at initial implementations of these gauge theories, right? And I will tell you about two of, I mean, there are tons of early experiments that I really like, but two that introduced me to this field were this science paper from the group of Fred Jędrzejewski from 2020 and another from the group of Monika Eidelsbuga in 2019. So here in the first one, basically they use two species of ultra-cold atoms, lithium and sodium, Each will represent either the matter fields or the gauge fields. And what they did is employed in a building block, in a simple building block, so it wasn't a large-scale lattice. In a building block, they employed spin-changing collisions to mimic the the annihilation and creation of electron-positron pairs. On the other hand, in the experiment of Monica Eilers-Buga, they were interested in a Z2 gauge theory. So the one in Heidelberg, so the one on the left is a U1 gauge theory. The one on the right is a building block of Z2 gauge theory, where they used a double well potential. And by shaking it resonantly at the on-site interaction strength, they were able to get an effective Floquet Hamiltonian that has the Z2 symmetry that they want. But the problem with both these cases is the mapping, so the perturbative mapping that they do from the actual quantum system that you want to model to the quantum simulator introduces unavoidable errors. And you also have imperfections in the experiment. So an example of these imperfections would be if we focus on the experiment on the left. So as I told you, you have spin-changing interspecies spin-changing collisions that will mimic the electron-positron creation or annihilation. However, you can easily imagine a process where you have a sodium atom that gets excited. So think of these atoms, they subject them to a heavy magnetic field such that they're confined to a hyperfine manifold. So they become a two-level system. So you can imagine one of these sodium atoms gets excited without the lithium atom reacting. In the language of particle physics, what this means is you had an electron-positron pair forming without the electromagnetic field changing in between. And this violates Gauss's law. So for the rest of the talk, we will refer as H0 to the gauge theory that we would like to implement. So if we were gods of experiment and we had full control of nature, we would be able to implement exactly H0. But alas, we are mortal and we can't. And so we will always have these unavoidable errors, lambda H1, which at best are perturbative. And then you can show that you kind of are able to analytically connect through perturbation theory to gauge theory dynamics up to a time scale of 1 over lambda. But we would like to do much better than this. Pictorially, what happens is the following. I'm in the lab. I try to implement H0 and keep my dynamics within the physical sector. But now, because I have experimental imperfections, I will be driven to the total Hilbert space of the quantum simulator. And this is something that I would like to suppress. So to put this on a formal footing, let us again consider the Schwinger model, but we have this.
But can I ask you a question about this?
Sure.
Maybe first the devil's advocate argument and then the question. The devil's advocate argument is that when if one wants to perform a quantum simulation of these complicated theories, of course, one has to kind of achieve an accuracy of the quantum simulation that's like a smaller, an accuracy that's better than what could conceivably get for a classical simulation. That's probably hard to get. But anyway, my question is, could it be that the dynamics within the relevant subspace is like fine, and that only like the weight of the signal will be appropriately lessened, just like in a decoherence free subspace where the dynamics within the subspace is fine, but the entire space may decay, but the leaking out of the space may not be so problematic as long as the dynamics within the subspace is fine. So can one argue that it's okay when there's a bit of a leakage dynamics through H1 as long as within the green part things are fine?
That is a very good point, but unfortunately, this can happen, but in very, very specific cases. So like what you are saying is exactly true in the case of disorder-free localization that I will talk about later. So disorder-free localization involves dynamics happening in different sectors, but only inter-sector dynamic, only intra-sector dynamics, but you don't want any intersector dynamics. So indeed, if you are able to do this, that's great. Then your system, you can disconnect it into a bunch of simulations, if you wish, that are just not talking to each other. That's absolutely true. However, generic errors, even local ones that you find in the experiment, will couple these different sectors together, and then you have crosstalk. But that's a very insightful comment that you made, Jens, because our methods are exactly that. Our methods try to make the target sector itself, a decoherent free subspace.
Oh, okay, good.
We do this through the quantum Zeno effect. So
I see. So that was a good idea. Okay, good.
That was a spoiler, basically, on your part.
Oh, I'm sorry.
No, I'm just joking.
I'm sorry.
Quite nice. No, it's quite nice. But that's funny because that's exactly what we do, as I will show in a little bit.
Okay, wonderful.
And so now, to get you to exactly where Jens was thinking, let us consider the spin 1/2 formulation of the quantum link of the Schwinger model. This is called a U1 quantum link model. So it's just a fancy term of saying, I took my Schwinger model on a lattice, I took away the infinite dimensional fields, and I put spin S operators. And now the S plus, this raising spin operator, becomes your gauge field, and SZ becomes your electric field. And you see, all I changed in Gauss's law from the slide that I showed you earlier is I replaced the infinite dimensional E fields with these spin S operators SZ. Good. And now the experimentally relevant errors are of the following form. So these errors are really prevalent in modern experiments. And what this term here, S plus, tells you is it tells you have a process where I'm changing the electric field without doing anything to the matter field. And you also have this term where I'm creating or annihilating electron-positron pairs without doing anything to the electric field. And both these processes violate Gauss's law. Initially, what we did is we said, okay, let us make a ground state manifold out of the physical sector. So basically what we do is we introduce this energy penalty term GJ squared, because remember, I want to be in the target sector that I define as GJ equals 0. If you include this penalty and plot the infinite time value of your gauge violation, which I define as follows here below, this epsilon, and then you scan as a function of 1 over V. So here I'm fixing my error strength lambda, and then I scan V, right? So as you go to the right, V is decreasing, and you see you have a sort of chaotic regime in that a tiny change in the value of V will give you like a much different value in epsilon. But above a certain value of V, you get a controlled violation that scales as lambda over V squared. You can get this in degenerate perturbation theory. So your epsilon just plateaus at some point after a time scale 1 over V, and it plateaus to a value of lambda squared over V squared. And even though we did this in exact diagonalization for finite systems, we showed that this plateau persists also in the thermodynamic limit in this paper, where we used infinite matrix product state techniques. Good, but now the problem that you can notice here is that this term is experimentally very difficult to implement because it includes two-body multi-species terms, and we would like to have a simpler thing. Well, we know that GJ is a single body term. Can we just use GJ itself? Can we use the generator itself without squaring it? And the good news is that yes, you can. So you introduce what we call the linear gauge protection, which is nothing but a weighted sum in GJ, right? So you have these coefficients CJ that you slap onto the different GJ. And if you are able to tailor them in a smart way, you will be able to utilize the power of the quantum Zeno effect. So the dynamics, you can prove analytically that the dynamics will be described by the following Zeno Hamiltonian, which is nothing but the ideal model that you have H naught plus lambda times this term. And this term is the projection, is a sum of the projections of the error term onto the different sectors. What this tells you is the following. If H1 has only processes that take you from one sector to another sector, this term here will be completely zero. But sometimes H1 can have good processes, like gauge invariant processes, that merely renormalize my gauge theory. But up to time scales at least linear in V, you guarantee that you will have a gauge theory with the gauge symmetry that you are interested in. How this works is as follows. So even though I talk about the quantum Zeno effect, I'm not doing any measurements here, yeah? Everything is unitary, but this is the concept of continuous coupling, where instead of measuring frequently, you just have a term with a large energy scale, which is this guy Hg. So I slap a big V onto it. And what I wanted to do is I want to spectrally decompose it into non-degenerate eigen operators PM, where each projector PM is, so these are eigen projectors, and each projector PM projects you onto a given physical sector, onto a physical gauge super selection sector. One of them will be your physical sector. And here it depends on how rigorous, how thorough you want to be. If I really want to protect dynamics in each and every sector, then you better satisfy the following relation. So here, you want the summation over CJ, GJ to be different than this summation in another target sector. What this means is that any two sectors will be represented by eigenprojectors that have different eigenenergies. So what this does is, up to times at least polynomial in V, it will suppress any intersector dynamics, but it will leave the intrasector dynamics that we desire completely untouched. However, in a real experiment where you only focus on one target sector, I mean, we may focus on several gauge sectors, but let's say I only want to focus on the physical sector, we can show, at least numerically, that Cj is enough to be -1 to the j. Why? Because you only want to spectrally separate the target sector from all other sectors. Other sectors can mix as much as they like. I don't care. I only care about the fidelity of the target sector. And this method, we were fortunate enough to be able to implement it directly in a quantum simulator. And this figure here from a Nature paper that appeared in 2020, we were able to map the U1 gauge theory onto a tilted Bose-Hubbard model. Okay, so the screen froze a little bit. I'll just repeat the last couple of seconds. So we did a mapping of the U1 quantum link model where we used a spin 1/2 representation of the gauge field and the electric field. We were able to map it on a Bose-Hubbard model, where you can show up to second order in perturbation theory that you really get a very stable U1 gauge theory. And here, the shallow sites now represent matter fields, while the deep sites represent, when you fill them with doublons, they're basically an electric field, right? You have this electric or vacuum rather that points either to the left or to the right. And what we did is we performed a sweep through the Coleman phase transition, which involves the spontaneous breaking of a global Z2 symmetry connected to the charge and parity symmetries of this model. And we were able to go from the charge proliferated state, which is a Z2 symmetric state, all the way to one of the two vacua. We got spontaneous symmetry breaking and we got one of the two vacua. So these are all experimental results. And we were able also to measure the gauge violation over time. And as you can see, it's relatively well controlled. Good. And again, I insist that you can show in perturbation theory that you effectively get the following term in your Bose-Hubbard implementation. From your Bose-Hubbard implementation, you get the following term where Cj is complicated. It's not like -1 to the j, but it's very experimentally feasible, obviously, because we did the experiment. We then took this model and we did quench dynamics on it. And we probed thermalization and gauge theories.
Sorry, could you go back to the previous slide where you show the violation? Yeah. What does the vertical line and the dot
So these are errors. So the dot that you see, or the square rather, that's a measurement of the gauge violation. So you see it's always below 10%, but there's an error margin. So it can be, you know, anywhere along this dash. That's an error bar, basically.
I see, because it seems to me that the curve is like deviating a lot from the.
Yeah. I mean,
that's well observed. It's really, it's quite deviating. That's right. Mm-hmm.
Yeah, that's true. But I mean, you see here we are within the error bar. Here it gets tricky. I mean, don't forget we're reaching 120 milliseconds.
I see.
Which is quite impressive for modern quantum simulators, right? So if you want to stay at much shorter times, I mean, we can claim even better results, right? So here, yeah, we're deviating, but in a much better way from
Could you illuminate us theorists a bit about how or like what the standard is? Like, what do you mean by like a good time? Like,
yeah, well, I am a theorist too, so I should have brought an experimental colleague with me. But basically, you want to reach a certain time before decoherence take over.
Yeah, okay. Makes sense.
Very close to something very close to the vacuum, right? Of course, you're not going to get exactly to the vacuum because, you know, you're ramping through a critical point. So it's not going to be a perfect phase transition. But nevertheless, we do see the dynamics that
I see.
that we anticipate. And here the gauge violation, how we measure it is by actually making projective measurements onto the sites. And there we know what configurations Gauss's law allows. So we see the probability of these guys, and we see also the probabilities of the processes that are not allowed by Gauss's law. And these are the violations that we show here in this plot.
I see. And could you tell us like what this time corresponds to in like hopping time in terms of units of the Hamiltonian?
That's a good question. So here, like you're hopping, that's the problem. Your hopping is changing itself because in the sweep that we do, you're changing not just the mass, you're changing the mass and the hopping term. But in the next slide, I can show you what
Okay.
answer your question. Because
Okay,
there we
thank
do
you.
quench dynamics. So basically, yeah, here. So we do quench dynamics. And as you see, here we have thermalization, right? So basically these oscillations are going to get damped. And here what we did is we used the setup and we showed that if you start in generic initial states that have in common only the initial quench energy, they're going to thermalize to the same steady state, or they're going to relax to the same steady state, which one can adequately describe by a thermal ensemble. So knowing, all you need to know is the energy of the initial state, and then you can describe, you see that you go to a steady state that you can describe with a canonical or microcanonical ensemble. I mean,
Yeah.
So here you see some oscillations, okay? But of course the oscillations get damped because of thermalization. But I have a better slide for you that will make you happy. And so here we investigated thermalization. And what I want to mention is that this is an important topic in gauge theories because thermalization in gauge theories like heavy ion and proton collisions, these are really open questions. So here it's, of course, a really teeny tiny step, but in a direction where we are hoping that these thermalization questions in gauge theory can be probed on a quantum simulator. And this paper appeared earlier this year in Science. Now, to answer your very nice question, look at these times that we reach and look at how many oscillations we have, right? So you can count them. But here we didn't start in generic initial states. We started in the vacuum of QED. And you see that we have this really robust scarring that you see here. So this is the magnetization, or you can think of it as the order parameter of your model. The flux, many names, but all mean the same thing in this context. And you see we have these persistent oscillations up to really long time. So we reach 150 milliseconds. And we also showed in a recent, so this will hopefully appear in PRX soon. And here in a theory paper that we did in PRB, we showed that if you add a driving mechanism, you are able to enhance these scars even more. So I'm not saying anything bad about the Misha Lukin experiment. It's an amazing experiment, but as you can see, we have much better agreement between theory and experimental results here because of this linear gauge protection term that I discussed earlier. So this linear gauge protection term really stabilizes your gauge symmetry. And this allows you to have much better persistent oscillations. So in another work, this one here at the bottom, which will appear in quantum, we actually showed that to get scars, stabilizing the gauge symmetry is a necessary condition. If you start doing perturbative errors onto the gauge symmetry, perturbatively breaking it, you see that your scarring starts deteriorating quite prominently.
I see.
So,
thank you.
You're welcome. And so, as a last slide on these experiments, we recently also proposed adding a term, the topological term that I discussed earlier, which shares a lot of commonality with quantum chromodynamics. So this term here, if you think about it a little bit, it's nothing but an explicit symmetry breaking term. It explicitly breaks the global Z2 symmetry. It doesn't break the U1 gauge symmetry. It breaks the global Z2 symmetry of this model. But what this does in reality is it introduces a confining potential. So what happens now, because of this term and because of the electric field becoming kind of an energy penalty for an electron-positron pair to spread, you end up getting confinement. And what we showed in DMRG simulations is that in the deconfined case, if you have an electron-positron pair, you see like a ballistic spread, basically. You see here a linear light cone. But now when you add a confining potential, you see that your electric field kind of just beats around a little bit. So the electron-positron pair, it just beats around a little bit, but it's basically confined up to all times that we can access in DMRG.
That's
so
interesting. But the direct sum structure you mentioned at the very beginning, that's coming from the actual gauge symmetry, right?
The what? Sorry,
the direct sum structure you had at the very beginning.
The dark structure.
The direct sum structure.
Are you talking about the
the-
gauge?
The
the
super
block-
selection blocks,
the super
right?
selection blocks.
Ah, the blocks. Yeah. So wait, let me just go here to. So you mean, yeah, we're working in just one block.
Ah, that's my question. Thank you. Sorry,
Yeah,
I should have said block, not yeah. I
No
meant
worries.
yeah.
Yeah. So, but indeed, you even in this simulator, I mean, I can measure the gauge violation for you, and you see a tiny gauge violation. So in DMRG, we get something like 1%, right? I mean, in the experiment, it's worse because of, you know, it's the experiment. But here you see that you are you have a well-controlled error, but it's within a certain error bound that you can determine from our linear gauge protection term. Like it depends on your effective V penalty, right? The error will go as 1 over V squared. But it's well controlled. It's not like increasing over time, and that's what we care about. It's plateaued. And we still see physics that we, so in this paper, which will appear in PRX Quantum soon, so this one here, we benchmark this to the actual U1 quantum link model, and you see like the same color maps, basically. The same heat maps, sorry. Good, and here, how we implemented this term in the actual experiment, or how we are implementing it in the actual experiment, is to add an additional staggering potential. So if you remember, for the non-confining experiment, we just had one staggering potential between the matter fields and the gauge fields. But now you see I add another staggering potential between the gauge sites themselves. And that's how you get this confinement. So we're really excited about having this experiment out in the next year, I guess, or something. But now, good. So harking back to Jens's question, we basically have been talking about working in the physical sector all the time. But what about doing what Jens said before? If we can have like all these different sectors and we have the dynamics working in them and they're not leaking to each other, you know, do we get something interesting? And the question and the answer is absolutely. Interesting. So high energy physicists will tell you this is rubbish. You only have one gauge sector that you work in. If you pin yourself to one gauge sector, the others make no sense. But we also do condensed matter, right? And so we're interested in exotic stuff, even if it comes from a gauge theory, it has no relevance to high energy physics. And so here, let me show you the following. Here I have two states. Both of them are domain walls in matter. But the difference between psi naught Z and psi naught X is the alignment of the electric field. So I align the electric field of psi naught Z such that it's in a single homogeneous gauge sector, just in one of them. On the other hand, psi naught X, I align the electric fields in such a way that it becomes an extensive superposition over all your gauge sectors, or over a superposition over an extensive number of gauge sectors. And now what happens is I want to do a quench. I want to quench each of these states separately, and I want to see how the matter imbalance behaves. So we have this imbalance. What I mean by imbalance is basically the difference in matter occupation between the left and the right halves of the chain. If this goes to 0, then this is indicative of thermalization. If it doesn't, then we retain memory of the initial state, and therefore I have a form of localization. And what you see is indeed, if you start in psi naught Z, which is in one sector, you thermalize as you expect. So your imbalance goes to 0, and here in exact diagonalization, I go to really long system sizes, to really long times. On the other hand, if I start in psi naught X, the superposition state, you see I retain memory of my initial state. The imbalance goes from 0.5 to something close to 0.28 and stays there up to all accessible times. The way this was interpreted in these two really nice papers from the Misna and Skavdikio groups is that the superposition over the different gauge sectors induces a dynamical kind of disorder. Why do you get this disorder? How do you get it? Well, think of it this way. Each sector has a different distribution of background charges. And now when you create an initial state that is a superposition of these guys, you're kind of inducing a disorder over the associated background charges. And this is what becomes a sort of disorder in the Hilbert space, an effective disorder that leads to localization. Great. But here I showed you a very idealized case where I'm assuming that H0, the ideal H0 is there in the experiment and there are no errors. But
actually, to be sure, I mean, like, sorry, that's a very stupid question, but to be just entirely on the safe side, I mean, to be clear, I mean, it's just like disorder in the sense that you have localization, but it's like, there's no literal disorder. It's like 1 year Stark localization, and that in effect,
that's That's what Stephen and I will be investigating with you, actually. Like, this is the thing. I mean, I talked to Stephen about it, and we wanted to discuss this with you.
No, fine, but it's still true that, I mean, there's no literal disorder.
No. That's the thing. That's the thing. So if you work with the Schwinger model itself, so there's a paper, I think, in this paper here. If you work with the Schwinger model itself, what you can do is you can integrate out the gauge fields completely, right? You can use Gauss's law, and in the limit, when the gauge fields are infinite, you can actually integrate them out, and then you get an effective spin model where you only have the matter fields as spin operators. And there you see that your gauge coupling strength becomes an effective disorder strength. So you really get a term where you have disorder over the matter sites, and this disorder is in the term of the background charges. But the question is, how can we define lyons there, or L bits that are exponentially localized? That's an open question that was not investigated. And if you do this mapping that I told you about, integrating out the gauge fields, this kappa term, this gauge coupling strength, is also a coefficient of a confining potential. So the question, so you may absolutely be right. You may absolutely be right that there is disorder, but it has not, it's a weird kind of correlated disorder. So it may not be leading to localization, and it may all be this confining potential that you have.
Oh,
and
now I get the kind of seeming disagreement in my head. Okay, now I'm fully with you again. Okay.
Yeah, great. But this is actually a really nice question that I think the flow equations method will actually bring an answer to. So let's see.
Now I see the kind of story. That might well be it's kind of cute in that it's basically a classical simulation resolving a crime story of a quantum simulation, but never mind. It's really interesting.
Yeah.
May I ask a question regarding what you just explained? So I'm with you with like the effective disorder. I mean, the gauge degrees of freedom in the end are, depending on the perspective, just an effective mathematical tool, and like on the pure spin level, then this gives you some disorder. But the correlation in the disorder that you were mentioning, is this due to like the Gauss law, that like the global gauge constraint enforces like on the disorder level, like some correlations then?
Absolutely, yeah. Because if you think about it, your Gauss's law involves a matter site, involves only one matter site, but it also involves the adjacent electric fields on the neighboring links. But these links also take part in other local constraints. So all these local constraints are in a way correlated to each other. And then when you integrate out the gauge fields, you get a kind of scary looking effective model, spin model, which has a confining potential, as I said. And also it has this disorder term. And that disorder, so you have the background charges on different sites being slapped onto matter sites far away from them. So it's something like all the background charges to the sites left of your site will also be involved in the potential for that matter site.
Okay.
Yeah.
Cool. I mean, that makes sense. Yeah.
Yeah. Good. And so let us look at what happens if we introduce these experimentally relevant errors, right? Because we are interested in actually making use of disorder-free localization in quantum information technology purposes. So there we will have errors. Let's see how these errors behave. And now I will introduce these errors lambda, right? And again, I will start in the superposition state, and I will repeat the same quench. So you see, whereas I have stable finite imbalance for all times in the ideal case, if I add a tiny perturbative error, which is 100th of the coupling strength, you see that I lose all kinds of localization, or I lose any trace of it. I don't have any kind of plateau, and I just go to zero in the long time limit. And this is something that we would like to remedy. And so we turn to our linear gauge protection scheme that I told you about. And here's what happens. So schematically, these lambda terms here, these error terms, are causing crosstalk between the different sectors. So this is equivalent to if you think of an MBL system and you have a time-dependent disorder, in the end, you will delocalize. And this is exactly what's happening here. So we introduce our linear gauge protection. And as I told you earlier, this takes the faulty theory into the effective Hamiltonian that you see here, up to times at least linear in V. And we took a CJ that is very simple, just -1 to the J, right? Because we also want it to be homogeneous, a homogeneous sequence. So we didn't want CJ to be disordered, because then if you get localization, it may be due to that. And what happened is the following. This protection term kind of suppressed it did suppress the intersector dynamics, but it left the intra-sector dynamics untouched. And without further ado, here are the results. So the yellow one is the ideal case. The red one is when I introduce the error, but now I introduce the protection strength, V, and you see that I restore the plateau up to times quadratic in V. As you can see here, as demonstrated here in the inset. I collapsed them onto each other at the time scale proportional to V squared. And so we are able to stabilize this order-free localization. And what we showed in an upcoming work, it will be published soon, this one here, is that basically if you make Cj a Stark potential, so you just add J times -1 to the J, so it's site dependent now, you are actually able to stabilize it for all times for relatively very small values of V. So here you see V over J, if it's 1, you go to really impressive times like 10 to the 4 over J. But with V equals 1, and if we introduce the Stark gauge protection term, we are actually able to access really long times. So we stabilize it to all accessible times as well, which is quite interesting. Though some people may tell you, okay, but you have a linear potential. Is this really disorder free or not? We think it is just similar to Stark MBL. Okay, great. So do I still have time actually? I need maybe like 5 more minutes.
Yeah, go for it.
Great.
If
So
though we will not cut short your like smoking gun. So
thank you.
Sure not.
So basically now I've shown you a lot of works where we did a nice scheme involving only the generator itself, a single body generator, and that really stabilizes my experiment, my quantum simulator of the gauge theory. It stabilizes it up to really long times experimentally and numerically. But now, what about if we look at a gauge theory like the Z2 gauge theory, where its generator is a nasty 3-body term? Remember, the U1 gauge theory, it's a single body term. Now I have a nasty 2-body term. And so if you want to do linear gauge protection here, you're kind of screwed because this term is extremely hard to implement experimentally here. So if you look at the Z2 gauge theory, let us introduce it quickly. The A's here are your bosonic operators. They represent matter. Tau Z is a Pauli matrix operator that represents the gauge field. And Tau X is a Pauli operator representing the electric field. So this is the generator of Gauss's law. And because it's a Z2 gauge symmetry, it has only 2 eigenvalues, +1 and -1, obviously. Now, errors inspired from the experiment of Monica Eidelsbuga, so we found this in her supplemental material, take the following form, and they all break gauge invariance. So what do we do? How do we protect? How can we utilize this generator or a variant of it in order to protect gauge invariance? So we came up with the idea of a local pseudo generator. We said, okay, look, this generator GJ is to generate the Z2 symmetry with all these different sectors to build them in a very specific way. But I only care about the physical sector. So we introduced the so-called local pseudo generator, where we split this full generator GJ into 2 terms. And GJ tar is the target sector that you want to be in. Do you want to be -1 or +1? Because these are the only 2 options in a Z2 gauge theory. And what you find here in this table is if I choose that I want to be in the target sector -1, then you cannot distinguish between WJ and GJ in that sector. So whenever WJ has an eigenvalue -1, GJ has an eigenvalue -1. Similarly, if you want your target sector to be +1, whenever WJ has an eigenvalue +1, so does GJ. So in principle, what this pictorially means is that when you are in the target sector, you really cannot tell the difference between GJ and WJ. And now you can extend our concept of linear gauge protection to the pseudo generator. So instead of having summation over J, CJ, GJ, now you have summation over J, CJ, WJ. And interestingly, which will be vital in our next slides, you find that the symmetry due to WJ actually is richer than that due to GJ. So WJ has a symmetry higher than the Z2 gauge symmetry that we have in our original model, and it contains it. How can we apply this to enhance this order-free localization? So if you look here, again, I have the faulty gauge theory. And now I add this protection term to it. What this protection term does is not only suppress these intersector dynamics, but it also generates effectively a new symmetry expressed by these green blocks. Now put yourself in any one of these green blocks, you see that right away you are in a larger yellow block, right? So that means the green symmetry, let's call it the green symmetry, includes the yellow symmetry, which is the Z2 gauge symmetry. It includes it. Now, what does this mean? All this means is if I prepare my state in a superposition over an extensive number of super selection sectors, now the superposition is not only over the yellow blocks, but also over the green blocks, which means I have a greater effective disorder over the background charges simply because I have more effective sectors that I'm working in. And what this does to disorder-free localization is massively enhancing. So you see, whereas the ideal case would give you the yellow line and the erroneous case would give you the red line, once you add the linear protection term with the pseudo generator, you get the green line. So you have greater disorder, which means you have greater localization and greater retention of the initial state, of the memory of your initial state.
So could you go over this logic of the green blocks again? It was a bit too fast.
Sure, no worries. So H0 is your ideal theory. It has a symmetry generated by GJ. It does not have the symmetry generated by WJ. Actually, H0, the ideal theory, does not commute with WJ. So here, let me go back to this slide. So WJ, the pseudo generator, it does not commute with this Hamiltonian. It doesn't.
Where does the pseudo generator come from?
Okay, so this is what I motivated earlier, but I'll go over it again. So
Yeah.
H0 commutes with GJ because
Yes,
it has a Z2 gauge symmetry.
that's right.
The pseudo generator comes from an experimentally inspired side. So what we say is GJ is terribly difficult to implement experimentally.
Right.
WJ is not. WJ is feasible in Rydberg with Rydberg atoms. And so what we say is we extend the concept of linear gauge protection. Remember, we used to have summation over J, CJ, GJ. That was the whole linear gauge protection.
Yes, that's right.
That's right. Now we say, let's change that by replacing GJ with WJ. Because
okay.
because WJ, I can implement it in an experiment. So I can use this guy in a real experiment to stabilize my gauge theory. But what it turns out is WJ has a symmetry that is richer than that of GJ, richer than the symmetry of the original model. Now, if we go to the next slide, even though the original model H0 does not have the symmetry due to WJ, once I add this linear gauge protection term in the local pseudo generator, I get an effective theory that includes the symmetry. So the effective theory that arises will include both the Z2 gauge symmetry, but also the symmetry generated by WJ, which is richer and
by that extra number, like number operator, right?
Sorry, say it again.
The extra number operator. I mean, that's the difference, right?
No, it's not extra. So here you have -1 to the NJ here, and I just
but you have this extra number operator, right?
I don't know what you mean by extra because it's here already in GJ. So it's not an extra. I just re-represented GJ in such a way that WJ has to act like it only in a given target sector.
Okay.
That's the crux of the argument, basically. So I want to be able to energetically isolate a target sector from all the other sectors here represented by red. To do this, I don't need a GJ. I just need any operator that acts exactly like GJ within this sector.
I see. They exactly coincide on that sector.
Exactly.
I see. Okay.
Exactly.
I see.
And outside of this sector, what happens is they're not the same, right? That's why you have like here multiple blocks instead of one block that's overlapping. In the target sector, you have a green block overlapping the full yellow block. But here I'm showing you what this does in the other sectors, and this is exactly what enriches the physics. So if you only work in the target sector, like what I was doing earlier for the scars, you're not really gonna see, the only advantage you have is that you have an experimentally feasible scheme in the local pseudo generator that can stabilize your gauge theory.
That's right.
But you really would not know if you're using WJ or GJ, right? the experiment will be the experimentalist will, because it's much harder to implement GJ. But if you're like just observing the experiment, you will not know if inside they're using GJ or WJ. But now once you go to dynamics comprising all the sectors or an extensive number of the sectors, you will see the effect of WJ, because in the non-target sectors, WJ will show you that it's generating a much richer symmetry. And
okay.
Exactly. And this is embodied in these green blocks that I represent here schematically. So in one yellow block, you have a lot more green blocks. And this is just a lot more charges, background charges for your effective disorder.
I see.
Exactly what leads to this.
I see. Okay.
Yeah. And in this paper, which is now published in PRX Quantum earlier this year, we proposed an experiment using Rydberg atoms. The power of this approach, let me just emphasize this. The power of this approach is that you don't have to use a bottom-up approach. You use a top-down approach in constructing your gauge theory. So rather than trying, okay, look, I have the Z2 gauge theory, I want to implement it exactly with gates and whatnot, and I need to worry about a whole bunch of stuff. What you do is you simply implement your LPG term, your local pseudo-generator term. And this is what we pictorially show here in a Rydberg setup. You just arrange the atoms, so the blue ones will represent a gauge and the gray ones will represent matter, or vice versa. And now you arrange them in a certain way that you get your WJ, you get your pseudo-generator term just by the geometry. And what you do is you perturbatively drive your atoms. Now this perturbation, what it does is it induces gauge invariant dynamics between the different sectors, but also gauge invariant dynamics that couples these sectors, which we don't want. But we don't care about the gauge invariant dynamics because our pseudo-generator technique is so powerful, it will suppress these gauge non-invariant errors, but it will leave the gauge invariant processes untouched. And so you get an effective renormalized theory with a Z2 gauge symmetry that you want, but it may not be the ideal Z2 gauge theory that you started out with. But you can do some engineering to get that. But what we say is, at least for these proof of principle studies, we don't care. We just want to show you that we are able to have a gauge theory with a Z2 gauge symmetry that we can control. Good. And we extended this method to 2D in a paper submitted to Nature Physics, where we were able to study the Schwinger effect. And again, disorder-free localization in 2+1D, which is really hard to do classically in exact diagonalization, and nobody has studied before. 2 dimensions with dynamical matter, that is. And so as a conclusion, I reach here the conclusion. What we did is we showed in this talk how gauge invariance on quantum simulators can be enforced cheaply and effectively using really simple protection terms, right? What I call the linear gauge protection, which you can use either as a function of the full generator itself, in case it is simple, composed of single body terms, or you can simplify the generator. If it's really complex, you can simplify it into local pseudo generators. And this is valid for a wide variety of generators. You can always find a pseudo generator that approximates your generator, your full generator in a given target sector. We showed that salient features like many body scars and disorder-free localization can be greatly stabilized and even enhanced by these linear gauge protection schemes. The outlook for the future will be to probe high-energy salient features such as confinement. Here, the plot that I show you is the work we did with Google AI, Google Quantum AI, where we studied confinement and a Z2 gauge theory. And what we want to do now is we want to extend these works to non-abelian gauge groups and also to higher dimensional higher dimensional gauge theories. As Jens said, this is of course very important. Ideally, the holy grail of this field is to go eventually to 3+1 dimensional quantum chromodynamics, and we are taking small baby steps towards that end. But basically, we're excited and we're optimistic. So. Finally, if you want a quick, dirty outlook on what I just told you, there's this summary paper, a review paper that we did as an invited contribution to the proceedings of the Quantum Simulation for Strong Interactions workshop, where we basically summarize the majority of what I told you here, albeit briefly. But inside you, if there's any topic that you are interested in, we have the links to all the relevant papers. So thank you very much, and I'm open to further questions.
Wonderful. Thanks for this amazing talk. Like this
Thanks, Jens.
extremely impressive
Thank you
talk.
guys for the
Anyway,
really nice questions, actually.
that was really great. And we had lots of questions along the way. That's also great. Thanks for this.
Yeah.
That's very nice. So are there more questions? Yeah,
I may have a question actually. So when you run like the first part of the talk, you were showing that the revivals of this Lakshmi take or like fidelity probability, right?
Yeah.
Do you have like did you explore what would happen if you if one starts from like a mixed state instead of a pure state?
Actually, yeah. So we did something like this. So it depends on your mixed state, right? So this is something that we put out a couple of months ago, which we call temperature-induced disorder-free localization. So we prepare our system in a thermal ensemble that is at 0 temperature, a pure state in a homogeneous gauge sector. But now once you increase the temperature, you start populating more and more sectors, and you see that you actually get disorder-free localization there. Now you're asking about quantum many-body scars. So this is something that I am doing now with the Slatko-Papic group. We are looking at similar ensembles in the PXP model. And what we find is we find great robustness of scarring at finite temperature. So we go to quite high temperatures. And yes, I was also very surprised because, you know, in principle, what you have is you have these two vacua, degenerate vacua. And if you start in any one of them and you do a mass quench, basically you get these nice revivals, right? But if you choose any of the excited states in between, you get weak scarring. And so I thought if you started in an ensemble, you will get these so-called intermediate vacua, but at the same time, you will get a lot of inhomogeneous states that will basically completely kill your scarring. But it turns out that the scarring was quite robust. And we're trying to actually understand this better analytically now. That's the only thing, that is delaying us from putting the paper out. So, yeah.
I see. And what figure of merit did you compute in the case of mixed states, like somewhat states?
So we did the so-called interferometric return rate. So this is something.
Sorry, the what? Sorry.
We call it the interferometric return rate. So
okay.
I mean, I can send you details later over email if you wish. Just shoot me an email or something. But basically, it's just a generalized form of your fidelity.
Right.
But this was also used quite a bit in the context of dynamical quantum phase transitions at finite temperature. So many groups, including us, we had to define several extensions of your fidelity to finite temperature. But this is the one that seems to be very natural, at least in the context of quantum many-body scars.
Thanks.
My pleasure.
I have a question. I mean, I suppose that many of these realizations that you have hinted at, and that was not in the focus of your talk so much, but they are effectively like Floquet-driven systems, right? To get these gauge theories in the first place.
The one by Monica Idles-Vuga, yes. The one by Monica.
In cold atoms, you get these kind of funny couplings. Presumably, you have to kind of be in a Floquet-driven setting. But you seem to be working like with Hamiltonians all the time. So, or your linear gauge protection scheme, which is like really cute, I must say.
Yeah.
This is very nice. But that kind of looks as if applied to a kind of static Hamiltonian setting. But is there anything to be thought about when you kind of apply that type of mindset to the Floquet-driven setting, which you are presumably doing?
Yeah, so basically, so if we have a system where we are really driving something, like not just in the effective theory, basically we have tried our stabilizers, static, even in their static form, and they do show some stabilization, but up to more limited times. So we are trying to understand this. So this is something that we have kind of put on ice for now, because there are a lot of other projects that take precedence. But this is something definitely interesting. And what we are thinking about is time-dependent sequences, CJ, that would basically vary in some harmonic of your driving to stabilize your theory. So
you're reading my mind, because that was actually my actual question that I wanted to ask, that whether this kind of extra knob that you can kind of turn helps you in these kind of stabilization.
It should. So we haven't investigated that so deeply yet, but this is definitely on the list. So we can definitely discuss more.
We should. That's kind of interesting because you could kind of use that kind of time dependence to get further stabilization in a way.
Yeah.
Okay, thank you.
My pleasure.
Wonderful. Other further questions?
I have a question about the frequency of the oscillations. I'm not sure if you mentioned already and I missed it, but do you have an understanding of what the frequency of these persistent oscillations depends on?
It depends on the spacing between these towers that I showed you earlier. So you can see
in terms of the microscopic, of course, this is, yeah, but in terms of the macroscopic parameters?
let me just go back to this too. Yeah. I hope I didn't give you guys a headache through this blitz through the slides. Good. Yeah, I mean, so this this spacing between the different quantum scars, this determines the frequency of these revivals. In terms of the microscopic operators, I don't know of a direct relationship. Yeah, actually there is none, because I mean we have tried different models in these two papers that I, in this long paper here. This will be the PRB and the PRL-PRB combination. So we tried the spin-S-U1 quantum link model, the truncated Schwinger model, and the spin-S PXP model. And there we were using like the same parameters in that we were doing a massless quench with the same tunneling hopping constant, and the spacing was different between them. So this is
it's not a universal kind of thing.
It's, yeah, exactly. But good question. Yeah, I mean, maybe there's something more intricate that we haven't found yet, but I'm not sure. I don't think so. Even, yeah, I mean, it seems, let me tell you this, it seems that the periodicity depends more on the spin length, excuse me, on the spin length that you use for the gauge field and electric field representation. So for example, for the spin-S quantum link model, it goes like proportional to 5.13 pi times S. Don't ask me why, but it's 5.13 pi times S. We verified this in finite systems and in infinite matrix product states. And also, but the truncated Schwinger model, I didn't explain it, but basically what it means is you have this infinite dimensional guy, you just crop it. You just crop it in the middle, right? You don't represent that piece with a spin-S operator, you just brutally crop it. And there you get something that is more like proportional to the square root of S times S plus 1, this period between the revivals, yeah. So each model has surely different frequencies of revivals, even when you are using the same parameters. Jens, I can't seem to hear you.
Yeah, you've mentioned along the way that the features that you see like are kind of enhanced to the emergent local symmetries. What does that mean? I mean, like, what does enhancement mean? I mean, after all, you're just kind of enforcing the local symmetries by your scheme.
Yes.
So what's the?
So the enhancement is here basically in this based on the concept of a local pseudo generator. So in particular here. So by enhancement, so as a general rule, enhancing the features of a gauge theory would be to kind of endow it with a richer symmetry, right? Because then you can just utilize the symmetry to get more exotic behaviors. And here is just one example, right? So you use the pseudo generator to start, you first start with an ideal theory in an ideal gauge theory with a Z2 gauge symmetry. Then you add this linear gauge protection as a function of the pseudo generator. And this endows your effective theory with a symmetry that was not contained in H0, and that H0 actually does not commute with it. And so now you have a dynamically emergent enhanced gauge theory after starting in a gauge theory with a lower symmetry. And this enhanced, in this particular example, it enhanced disorder free localization by giving us greater localization for the same money, basically.
Yeah, wonderful answer. I get it. Yeah, okay. I think I got both, but I didn't see the connection. Thank you very much.
But no, but I mean, that's actually a good point. So a good question to pose is, what can we use these local pseudo generators for beyond disorder-free localization, right? So right now we utilize it for local pseudo generators. Is there something that can be done for scars? And remember, I mean, here we can just become pure theorists, forget about the error term, and still add the protection term, and it will still enhance you. You know, without the errors, it will still do this enhancement. So we can look also at scars, see if this somehow enhances scars and other salient features, whether relevant to high energy or
even beyond. I mean, even the stuff you mentioned in your review article, right? I mean, even that might be well applicable beyond the regime of lattice gauge theories. I mean,
exactly. Yeah.
Cool.
Since you are showing this slide, by the way, I have one more question. So here you are working in finite systems, obviously, right? And you go to very large times because you do exact diagonalization. Is it important to check how the steady state value depends on the system size?
That's a good point. Yeah. I mean, we do finite size scaling. I am able to go, like in the case where I don't have errors, I am able to go to something like 16 matter sites. So effectively, it's like 32 spins in total if we're doing a spin 1/2 representation. And what you see is basically this plateau, like from 4 to 8, it decreases, then it increases for 12, and at 16, it's roughly in that area. So there's not like a functional dependence on the system size, but it's quite robust. And now, in still unpublished work, we actually are looking at disorder-free localization in classical systems. We're using automata, cellular automata, and we are able to go like to thousands of sites, and you see that it's very stable, basically. Yeah.
Thanks.
You're welcome.
Wonderful. Great. Yeah, very happy. Is there maybe a last question from the audience?
Well, then I seal the deal. Like this pseudo generators, I mean, these sectors, they reminds me of the generalized Gibbs ensemble when you talk about equilibrium problems, and I just wondering like if you do like a sanity check, if this thing does equilibria to like a generalized Gibbs ensemble.
We tried this. I mean, we tried this in these papers, and no. I mean, whether you do a canonical, microcanonical, or a grand canonical ensemble, you go to 0. When it comes, when it comes to the GGE, yes. I mean, in principle,
that's strange. One would expect. I mean, this is like constants of motion. One would expect like a maximum entropy state, given all the constants of motion. Is that not what's happening? That's interesting.
That is a very interesting question indeed. Yeah. Yeah, we have not looked at this. So, okay, so basically you're thinking the generalized Gibbs ensemble would just include these different GJs, these different WJs, sorry, as constants of motion in the constructed ensemble.
That's right.
And try to see if it, yeah. I mean, that's actually a good thing to investigate.
Because like, for example, like last year or so, I think I was playing with this with MBL, and they seem to agree like with the MBL. Like if you plug in the constant motions, and it seems like the local observables will just agree fine with the.
But see, that's a nice. Yeah. The thing is, again, the locals of motion, when it comes to this order-free localization, it's a bit strange because they're always there. Okay, but they depend actually on, like, if we think of the Schwinger model, they depend on your gauge coupling. So your gauge coupling has to be of a certain strength for you to see this localized behavior. Whether you have this localized behavior or not, these integrals of motion are always there.
But that's one more reason to carefully and quantitatively look at the L bits in that type of model.
Exactly. Yes.
That's a good advertisement.
Yeah. So Stephen, let's gear it up on that. Yeah.
Yeah, totally.
Good.
Nice. I would be intrigued to see what's happening there, because I would have expected what Bohan says is like generically happening. So
yeah.
One last thing, if you can plot the growth of entanglement, that would be great.
You can find it in the SPRX quantum.
You mean as a function
Okay,
of time,
perfect.
like
Oh,
faster than log growth of entanglement in time?
So it's no, it's quite slow actually. So
Yeah, but slow, but faster than log. No, it's like something a bit more than log or so. No.
Actually, I think it was a bit slower than log, if anything, like even close to a log. At least that's what we and other people found.
Oh,
yeah, but okay, but wasn't clearly log, right? I mean, some people argue it is. In our case, because we had to use smaller systems because we included errors, so we couldn't like take full advantage of the gauge symmetry, right? We couldn't work in like we couldn't separate the dynamics across different blocks. The blocks were talking to each other. So we saw remnants, like indications of a log growth. But if you go to the papers here, let me. Yeah, these papers here, Smith and Brennis et al., especially in Brennis et al. I mean, they really show log, at least in a teeny tiny part of the dynamics. You really see log growth.
interesting, because I mean, if I may say that even that relates again to the form of the Alberts, right? Because given the null, like if you must know that if you have like these in 2-norm exponentially decaying L-bits as your constant motion, then the entanglement can at most grow logarithmically in time. That's good, and nature seems to be saturating that. So that's a kind of a connection between the form of the L-bits and the maximum entanglement growth. Sorry, you can have in time.
I see. Okay.
Then what you say is even more interesting.
Okay.
Though I would say that, I mean, the other thing one needs to ask then is also that, I mean, if you have Anderson localization and you have zero growth of entanglement, but still your L-bits may be exponentially localized and not sharply localized. So,
No, that's
like,
right. I mean, it's only a one-sided thing. It can always be slower, as you say. And I mean, an Anderson localization means a flatliner in entanglement, and that you are absolutely right. Yes.
And in that sense, I wonder, like, would one, like, what's the interpretation of a log growth? Would it be like, well, it's not, I mean, there is a bit of quantum information flowing through the system, but it's essentially Anderson, or is it like more like, well, it's sufficiently many-body localized? Like, is there any consensus in the community how one would interpret such a thing?
Not that I know of. So still the question is still out, the relation between this kind of localization and orthodox many-body localization. And you know, there are people in the community who basically say they have nothing to do with each other, and that what we see here, or what was seen in this paper here by the Skardikio group, is basically maybe has more to do with the confining potential that you get in the Schwinger model once you integrate out the gauge field. So I wonder why they didn't like check that in that paper. You just need to turn off the interaction term and just like you do this artificially. It's no longer the Schwinger model, but you do it artificially, and then you can check all this. So this is something that we are working on now. And also we're doing this L-bit approach using flow equations with Stephen. So these are really new things that we just started. So we don't have answers yet.
Okay.
Yeah.
Wonderful. That's absolutely fascinating, and already a starting point of at least 2 ideas and projects.
Exactly.
So yeah, thanks for that again. Let's catch up soon. That's absolutely fascinating. Then thanks again for this wonderful talk, and thanks for the great discussion and the many questions, even on the day of a worldwide climate strike. So sorry for that. I was unaware of this.
Yeah.
So thanks again, and see all of you later. Maybe more than you would wish at the day of the QP deadline, but never mind. So thanks again to Jad for this wonderful talk, and see you around.
Yeah, it was a pleasure. Thanks, guys.
Yeah.
I really enjoyed it.
Yeah.